let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. It's the last official class of the semester. Tomorrow, I believe, is the last day of classes, and finals begin on Friday, I believe. Our final is on Monday. I'll actually talk about that a little bit later. Or maybe. Well, I'll remind you of the time. Last class for new material. So that's what we're going to do. As always, you're encouraged to turn your cameras on, participate, all that good stuff. And let's actually get down to this. Let's see if I can see the chat here. Awesome. Okay, so quick recap of what we've been doing. So lately we've been talking about the dot product and the cross product. The dot product is a scalar function. Well, yeah, I guess you could call it a scalar function. It's also called a scalar product, believe it or not, because when you take the dot product of two vectors, the result is a scalar. The definition is the following. You multiply corresponding components, add them together. Why would you do that? It turns out that that expression actually is a way to get the angle between the two vectors. And we saw that once we have the angle between the two vectors, we can also do things like find area using vectors. And that was very, very convenient. So the dot product is a scalar. So you can take two vectors of the same dimension, you dot product them, you get a scalar. And the point of that scalar is to really get to the angle between the vectors, the smallest angle. Now, if the dot product is 0, this means that the angle between them is pi over 2, because cosine of pi over 2 is going to be 0. So you can actually also use the dot product to test whether or not two vectors are orthogonal. Remember, orthogonal is our new word for parallel. So dot product has all these nice properties. We did a bunch of examples of that, finding areas between curves, taking dot products. We skipped the scalar projection and vector projection stuff, even though those are actually quite important in application. Moving on, we moved to the next guy, which was, let's make this a little bigger, which was the cross product. So now the cross product, this guy only works in 3 dimensions. So cross product as it's defined here and as it's defined pretty much anywhere else only works for 3 dimensions. The generalization of the cross product is called a wedge product, but most of you, unless you're a math major, will never ever encounter it. Most mortals only need to know about 3 dimensions, the cross product. Cross product is when you take a product of 2 3-dimensional vectors and the result is another vector. What is the other vector? The other vector is a vector that is orthogonal to both vectors in the product and whose magnitude is equal to the area of the parallelogram spanned by the 2 vectors in the product. It also follows the right-hand rule, which means if you take the cross product of A cross B, point your right hand in the direction of A, curl your fingers towards B, and put your thumb up, that tells you the direction of A cross B. So you might have to do this upside down or on a different angle, but make sure that you do it with your right hand so that it initially points in the direction of the first vector and your fingers will curl towards the second vector. So if A goes this way and B goes that way, I will need to actually turn my hand upside down in order to point it in direction of A and curl it towards B. So the normal vector would point down, the cross product. Okay, so the cross product, the point of the cross product is to actually find an orthogonal vector and a specific orthogonal vector, the guy that is the magnitude, whose magnitude is the area of the parallelogram. So a dot product gives you a scalar. The importance of this scalar is to find the angle between 2 vectors. If the dot product is 0, it means that the vectors are orthogonal. Dot products can work in any dimensions. As long as you have 2 vectors of the same dimension, the dot product is going to work. The cross product gives you a vector as a result. Sure, I wrote that in red somewhere. Cross product is a vector. The cross product gives you a vector as a result. And that vector is going to be orthogonal to both the vectors in the cross product at the same time. And we saw that being able to find a direction that is orthogonal to two other vectors is important for talking about the direction in which something is slanted in space. So that's why they're important. Also, I do expect you to remember what's in this box right here. So you should know A and B are orthogonal if their dot product is a zero scalar. A and B are parallel if one vector is a scalar multiple of the other. A and B are also parallel if the cross product is a zero vector. And another way to check that A and B are parallel is if the magnitude of the cross product is a zero scalar. Notice that the magnitude of the cross product is a scalar because the cross product itself is a vector. And so, yeah. So we went through a whole lot of stuff last time, deriving learning what a cross product is about, how to actually compute it. We actually derived the formula for the cross product from scratch. And then we also did a mnemonic for remembering how to write the cross product with a formula. And that's the formula. Now we are going to go through some examples right here. And then we're going to move on to the next topic. So let's move this out of the way here. Move this out of the way here. It looks like someone else needs to get in. Let them in. All right, boom. I actually want you guys to take a couple minutes and do this on your own. So I'll give you a couple minutes. I'll give you to like 5:45. Find the cross product of this guy. Tell me what it is. Okay, do we have an answer?
I got 4 in the I direction plus 7 in the J direction minus 6 in the K direction.
4, 7, minus 6?
Yes.
Okay, let's see. Did someone else said something?
Yeah, I also got that.
Okay, well, two of you got it. It's probably right. Let's see. So how do we do it? Caitlin also got the same thing. So yeah, A cross B. Remember how we do that? You set up this little vector right here. IJK along the first row. A goes along the second row, and B goes along the third row. Right away, you can put it in this form or IJK form, doesn't matter. But remember that the J part takes a negative sign. And so what we're going to do is we're going to block out everyone in the I column and J column, do that cross product thing. So we're going to get 4 minus 0. Then we block out everything in the J row and column, do the cross product thing. And we would get 2 minus 9. But we take the negative of that. And then we block out everything in the K column, do that cross product thing. We get 0 minus 6. And so 2 minus 9 is minus 7. Minus a minus 7 is going to be positive 7. So this is going to be 4, 7, minus 6. Yeah. So that's that. So essentially, if I had, let's suppose I had my A in this direction and my B in that direction. The cross product would do what? Would it point up or like down?
Wouldn't it point up?
Would point up. So this would be A cross B equals 4, 7, minus 6. By the way, if I were to create a parallelogram with A and B, what is the area of this parallelogram?
It's the same as the magnitude of the cross product.
It's the magnitude of the cross product. So it's the square root of 4 squared plus 7 squared plus 6 squared. Right? Yeah, so that's our first question. So we get an orthogonal vector. You know what direction it's pointed in. You also know how to kind of match this vector up to an area. So we have some computational as well as conceptual understanding of what this thing is doing. Awesome. Let's move on to the next problem. This whole thing fit? Okay, yeah. So the last one was 4, 7, minus 6. I think we're all in agreement there. Okay, so what if I ask you to do the following? Find a vector that's orthogonal to the plane that passes through these 3 points. Can someone tell me how they would do it? Ideas?
You could find vectors that would accurately describe the plane and then do the cross product of those 2 vectors.
Okay, how would you find 2 vectors that would describe the plane? So let's say I have these 3 points. So this is P. Say this is Q. Say this is R. And yeah, they're all in a plane. And I want to find a vector that is orthogonal to that plane. So how can I pull off what you just said?
You could take a vector from one of the points to another, and then from a second point to a third. So like P to R, and then R to Q, and then those two
P to
vectors
R.
would be on that
Okay,
plane.
so PR, what is that vector?
Wouldn't it be 3, 2, 5?
Yes. And then you said R to Q. It actually doesn't matter. You could also take P to Q, take Q to R. It's not going to matter, actually. And then, so right here, I just wrote RQ. RQ would be what?
-1, or sorry, -2, -1, -2.
Right. And so let's say here, I call this N for a normal vector. So how would we compute it now?
Now you do the cross product of the two vectors.
Okay. So PR cross RQ, which is going to be IJK PR 3 to 5 RQ minus 2 minus 1 minus 2. In fact, just because I don't want to kill myself here, just use the other one. Let's use QR. Because I'm cross-producting, I'm subtracting stuff. I don't want to have the negatives of negatives making me make a mistake. So let's just play it safe here. Yeah, so now you go in, you block out the I column. This will be 4 minus 5. Block out the J column. This would be 6 minus 10. Block out the K column. This would be 3 minus 4. And that works. We're not going to talk about this, but eventually you guys are going to want to be able to find the equations of planes, and you're going to need to be able to find a normal vector in this situation. So if you happen to know 3 points in a plane, you can find a normal vector to the plane by doing this exact procedure. I want you to know that any two vectors in the plane could be used. You will definitely get something that's parallel to this one direction that we found. So you could have made a different choice for your pair. It wouldn't have mattered. In fact, if I had made, if I use RQ instead of QR, I would just get the negative of this answer, which is parallel. So one normal vector is pointing up versus pointing down. It doesn't matter, they're still normal. Definition of normal is it meets at 90-degree angle. It doesn't necessarily matter what direction you're pointed in. At least not yet. There's going to come a point where the direction that the normal vector you're finding is pointing in is actually going to be important, but I'm pretty sure you won't need that until multi-2. Although I've never taught multi-2 at Fordham, so I don't know for sure. But usually something like that would come in a class like multi-2. Find a volume of the parallel pipe bed formed by blah, right? So we also saw that if I have 3 vectors, A, B, C, that if I do then the volume of this guy is the magnitude of the scalar triple product, which I briefly mentioned last time. And that is literally the magnitude of the determinant, if you like. Technically, it's one of the vectors dot the cross product of the other two, but it actually turns out it will be as if you're just taking a determinant with the 3 vectors lined up. So it's 1, 4, minus 7, 2, minus 1, 4, and 0, minus 9, 18. And because this could give you a negative number, you take the absolute values of it. So the negative is a matter of orientation. So it's not what we care about when we talk about volume, but that's basically going to be it. So here is where I lined up the vector A and did the vector B, then did the vector C. And determinants, we learned how to take those last time. So it's going to be 1 times minus 1, or it's going to be 1 times minus 18 plus 36, minus 4 times 36 minus 0, plus minus 7 times minus 18. So what we pretty much have here is what, okay, so 36 minus 18 is just 18. 36 is 2 times 18, so this here is actually 8 times 18, plus 7 times 18. So I have 1 times 18 minus 8 times 18 plus 7 times 18. That's 0 times 18. So it's actually 0. What this means here is volume of the parallelepiped is 0. I always forget how to spell this thing. I.e., the vectors lie in the same plane, so they don't actually open up. They're all in the same plane, so the volume of the thing that they span is 0. We call this coplanar. Okay, so all of these guys, the A, the B, the C, they're all in a plane. They don't actually span out to form the edges of a box. So that's another use of this, which, by the way, this is the same as A dot B cross C, which is a formula that we learned last time. It's in one of the properties. So cross products, pretty cool. We can use it to find an orthogonal vector to two given vectors, the magnitude of which is going to be the area of the parallelogram spanned by the two vectors, and it will point in a direction consistent with the right-hand rule. We can use this to do all sorts of things like find a direction that's orthogonal to a plane, or in the future, you'll learn how to do this to find vectors orthogonal to a whole bunch of other things. And one application is called the scalar triple product. You can actually find the volume of something. So if you know vectors that run along a certain edges of a three-dimensional parallelogram, which is called a parallelepiped, if you take the one vector dot product with the cross product of the other two and take the magnitude of that, you can find the volume of that guy. Of course, if the volume is zero, they're all flat in the same plane. And so, yeah, interesting stuff. Okay, so that wraps up this section. I don't think there was anything else. Yes, that wraps up this section. Yeah. So let's move on to the next section. So technically in your book, the next section is equations of lines and planes, but we are going to skip that, even though I'm going to talk a little bit about planes, because the thing I really want to move on to is some more sketches, because lines and planes you'll actually do in your other class, in the next class. Well, actually, a bunch of things I've already talked about you'll do in the next class as well. So here I also put some announcements just to make sure that we're all aware. So we'll take a breather before moving on to the next section. Let's try that. Okay. All right, so test 2 hasn't finished grading yet. I'll finish that later in the week, and I'll update that as soon as I'm done with it. Solutions are posted on Piazza, though. I think you all should have gotten like an email saying something to that effect. So full solutions, I explained everything, even for the problems where you didn't have to show your work. That's posted. Test 1 solutions, I also posted that, but I posted that such a long time ago, I don't actually remember where. If I didn't post that in Piazza, it's on the class website or something like that. But I posted that a long time ago. Final, you have to know, final's a week from today, Monday, December 14th at 5:30 p.m. So it's pretty much starts the usual time when our class starts. Just a little bit of info about the final, I guess I could say. Time, 2 hours and 15 minutes. 15 minutes is for upload. It's going to be about 25 problems. So normally in a test, I give you about 20 problems plus some bonuses. So you're going to have almost double the time, but only 5 more problems to do. You'll need to show your work for a lot of them. What else? It's cumulative. So covers material from both tests. Plus all 3D stuff. Well, up to today's class. What else do I want to say? Yeah, as usual, if you guys have questions on the material or on the solutions to test 2 or anything that has to do with the material itself in the class, I would recommend that you ask it on Piazza. It's more efficient for everybody. I can answer the question for one person. Everyone sees the answer. But yeah, so if you want me involved, that's how to get me involved with this. I would, at this point, especially, finals week is crazy for everybody. I'm going to get tons of emails all over the place. I don't want to miss anything. So I would only say you should email me if there's something very personal to your situation that you want me to deal with. But anything that's on the question about the class or the material, I would post it on Piazza. You can do this anonymously if you want, but there's actually no reason to actually do that. What else do I want to say? I think that's it for now, really. I didn't even write the final yet, but that's how I'm going to do it. So yeah. Any questions on that or anything else?
I have a quick question.
Yeah.
Is there any way, like any different way we could go about submitting the work? Because like both test times, I don't know if this is anyone else, but like it could be really super glitchy and then like it erases some of the work and it's like really frustrating trying to like take individual pictures. Like, is there any other way or is that just the only way to upload the work?
This is the, well, what I would suggest is the way I've personally used it, and I've never really had a problem with it. But I normally logged into 2 places at once. And the thing is with Gradescope is it always counts your last submittal. So I wouldn't recommend that you use both sources to upload the work. So what I usually do is I would log in on the computer and then log in on my phone. So my phone is the active submission thing. And I'd read the questions off the computer and do my work and then just take a picture of my phone and upload it on my phone. And I never switch between the two, or I never have to like open anything. And then it always stays current. So the only thing that I would say that if you keep having to like refresh something, it probably means that you're logged into 2 sources and one of them is playing against the other.
I had that same
So, yeah.
question. This last test, I tried to do the whole submitting on my phone thing, and it only let me submit on my phone for I think 1 or 2 questions. So I did submit my work on my phone for those, and then I refreshed the page on my computer and tried to submit it from my computer for the rest of the problems. And then when I turned it in, the work that I had uploaded from my phone wasn't uploaded on my final submission. So I'm not sure what happened with that, but I had some issues with uploading work too.
Oh, did you save it when you uploaded on your phone?
Yeah, I did.
And it didn't show up? That's strange. I think it didn't save. That sounds to me like it would have
Myself and a
saved.
couple other people.
And
I
I
think for me
would,
and a couple other people, it wouldn't give us the option to upload from anything but like a computer, which adds a lot of
no,
extra
that's
time.
not correct.
That's what it did to me last time.
Well, for the
Is
first
there-
test, I was
Yeah,
able
that
to
happened
submit
to
from
me
my
too.
phone. From the second test, I could only submit from my computer except for question, I think 17. It wouldn't give me, like I would click upload here and nothing would happen. I couldn't take a picture of it. I couldn't insert a document like I could in test 1. So I'm not sure what was going on, but that was my experience.
Oh, well, something is off there. And I wouldn't be switching between 2 platforms. Like I would just leave my phone to do the uploads. And I would
Is
never
there
upload
any
anything
way
from the
that we
computer.
could just like upload all, like, for example, if you write the notes on your paper, is there any way that we could just take like pictures of all of our notes at the end and upload it all to one spot? Just because like it's super frustrating and then like the time, it's just like a mess. Is there any way that we could like take a picture of our notes and upload it all in one spot rather than go back and forth on Gradescope?
That would make a lot more sense. The thing is, though, and I don't know if any of you are going to be teachers in the future, but when you're dealing with a class, it turns out that the thing that makes the most sense doesn't always work out that way. I did that last semester, just everyone upload in one spot all at once, and it was a disaster because students would be very disorganized. They wouldn't label their problems correctly. It took me hours just to organize stuff in order to start the grading. I may, I don't know. I guess I could put that as an option, but it would have to mean you guys would be very meticulous with labeling your work and uploading things in a legible manner. If I can trust you guys to do that, I can do that. But I've kind of been burned by that method before, so I'm very reluctant to do it. Like that's what last semester in this summer when I was teaching all my classes online, which between the spring and the summer, I taught, how many classes did I teach in the spring? 7. I taught 2 classes in the summer. So I taught 9 classes, so I went through this a lot, giving 9 finals, and it was always a mess. In uploading question by question is actually a lot more organized. I can grade faster, get the results back to you guys faster, and people tend to mess things up less, it turns out.
Yeah, I think if we just had the option to submit all our work in one place, maybe at the end or by email or something, it would be better in case Gradescope doesn't work again like it did last time to upload problem by problem.
I'd rather you upload to Gradescope. What I can do is I can amend the rules so that you guys can upload everything to maybe like the last problem.
I don't know if this helps, but in one of my other math classes, we upload just one document, but then we click which page each question number's on. So
yeah, I've also tried that. It doesn't, and sometimes that also takes a longer. I think what we could do is just everybody just decide to label everything correctly, like on the top of the page, you write Q1 or something. And so what I would say is I will allow it if we all agree to this rule. You do 1 problem per page, you upload them in order, and you label the problems. Do you guys think you can stick to that?
Yeah, that sounds good.
That sounds manageable.
Yeah.
Okay, I'm gonna trust you guys. You know, I've been hurt before by this. I told you guys, don't let me down, but I can do that.
What about 2 problems per page? Since it's 25 problems, that would be 25 pictures, 25 uploads. Would 2 be fair or just 1? Like if it's very organized, like very clearly labeled, this is question 1, box. This is question 2, box.
Yeah, I'll accept that, but you need to be. I need to not have to like, where's our question 5, and be like scrolling through a bunch of stuff. Okay.
Would that be then the new way to do it or an alternative way? Because I mean, personally, I haven't had many technical issues with the individual upload.
I'll set it as an alternative way.
Okay.
Okay. So I'll amend the instructions. I'll send you guys the instructions before the day of the final, and you read what your options for uploading is. So I'll still leave an upload link at the end of every problem, but if you had problems submitting it that way, you'll also have the option to just, at the end, just upload everything all at once. But in that case, you need to make sure it's organized, make sure it's in order, make sure it's properly labeled. Okay. All right. So and I'll only be doing this for you guys since you guys have been well behaved so far. Okay, so let's continue. Cylinders and quadric surfaces. So we're skipping another section and we're going to do this section. So this section is good and not so good in the sense that nothing really technical. It's going to be all about sketching, right? So like I said here, the focus will be on sketching. So this section is going to, in concept, be similar to what we were doing for ellipses and hyperbolas. So I just really want you guys to know how to sketch certain things. The thing is, though, it's going to be in 3D, and it usually takes students a lot of practice. So I don't think it's going to be hard, but it is going to be something that you're going to want to practice to get your hands on. So I will be asking you to sketch stuff, as well as looking at surfaces and identifying what equations go with those surfaces, etc. Matching equations with graphs, and matching graphs with surfaces, maybe even sketching something of your own as well. So it is something that's going to, I don't think it's going to be hard, but don't just not take it seriously, right? Actually put the practice in, or else you might have trouble with it. So we're going to learn to sketch things in 3D. That's what we're going to do now, which is going to be very helpful in the future. So that's going to be the focus. So it's not going to be super technical. Like I said, it's going to be very informal, kind of like how it was when I went over conic sections with you guys. I didn't expect you to find foci or anything specific. I just wanted to be able to do a rough sketch of certain objects. That being said, we did skip the section on planes and lines and planes, and I do want you to know how to sketch a plane. So I figured before we move on to cylinders and quadric surfaces, I will just take this part out of 12.5 and actually show you guys how to do this in passing. So the equation of a plane, I expect you to know one when you see it. So that's like this guy. A, B, and C are constants. X naught, Y naught, and Z naught are also constants. So you'll notice that if you plugged in numbers, so example, 3 times x minus 2 plus 7 times y plus 1 minus 3z equals 0. That is the equation of a plane. Anything that pretty much looks like linear from your intuition from single variable mathematics is going to be a plane when you go into 3D or higher. So the power of all the variables is only 1. They have constant coefficients, not all 0. So you can usually expand these guys and write it something like maybe, or say 5x plus 2y minus 3z equals 14, or anything of that form, or something like 2x plus y equals 7, right? These guys, which you would, especially the last one, you would think it interpreted as a line in Calc 1 and below. It is a plane in Calc 3, right? But that is the general form. And when it's written in this form, your ABC is a normal vector to the plane. So if your plane is here, your x naught, y naught, z naught is a coordinate in the plane. And a normal vector to the plane is given by ABC. Okay. So that tells you, for instance, when you have the equation of a plane, you can actually know what the normal vector to that plane is just by eyeballing it. N equals 2, 1, 3 is normal to this plane. Right? The coefficients of x, y, z tells you about the normal vector. So that's just a little bit about planes. You don't need to know any more than that. You'll learn a lot more about planes in the next class. What I do want you to know about, though, is how to actually sketch a plane. And you sketch a plane pretty much the same way that you would sketch a line in single variable calc. Find the intercepts, draw lines through it, right? So how did you sketch a line? Well, you find 2 coordinates on that line, and then you draw a straight line through those 2 coordinates. The thing is, for a plane, you need 3 coordinates. So 3 coordinates not lying along the same line, and then you draw lines connecting these coordinates. As usual with lines, It's not always possible, but if it is at all possible, the best coordinates to choose are the intercepts. They are also the easiest ones to find because the intercepts will occur when all variables except one usually are 0. So let's say I have, I want to sketch this. Right, so here's a plane. You look at that, 2x plus y plus 3z equals 6. You should recognize that as a plane because it looks linear. And it has all the variables there. But honestly, it can have, even if the y and the z weren't there, it would still be a plane. If any one of these guys weren't there, it would still be a plane, etc. Right, because it would still fall in line with the thing. So A, B, or C cannot all be 0, but you can have up to 2 of them being 0 at the same time, and it's still a plane. Also, if I think that's all I want to say. Okay, so what you would do to sketch a plane, find intercepts or 3 convenient points and connect them with lines. Okay. And I'm going to need more space. Okay. So for example, for this plane here, remember on the x-axis, both your y and z are 0. On the y-axis, both your x and z are 0. On the z-axis, both your x and y are 0. So to find intercepts, what that amounts to is plugging in 2 variables equals 0 at a time. So I could say set x and y equals 0. Immediately, you'll see that z equals 2. I can set, say, x and z equals 0. Immediately, you will see that y equals 6. I can set y and z equals 0. And I would get x equals 3. So set 2 variables equals 0 at a time. Solve for the third. Right, so just like in 2D, you wanted to find the x-intercept, you set y equals 0, solve for x. Want to find the y-intercept, you set x equals 0, solve for y. Same idea applies here, except you have 3 variables to worry about. So in order to solve for 1, you have to set the other 2 equal to 0. You don't have to write this out, though. You can literally just look at this and do it in your head. Like I don't think me or I don't think anyone else, or anyone else would actually expect you to write this out. You should be able to just look at the 2x plus y plus 3z equals 6. In your mind's eye, set the y and z equals 0. Okay, x equals 3, y equals a, and then you immediately do it. You don't have to write this out. So what do you do now? Well, as always, you're going to draw your axes. And now, right, so, you know, no one hits negative, so we don't even have to draw these, but we're going to plot all the points that we found. So we found that z was 2, x was 3, and y was 6. Found the intercepts. And now what we do is we just connect those with a line. So that's your plane. At least that's the part of the plane slicing through the first octant, which is often where you're going to want to draw things anyway. And of course, this is a plane. So you should understand conceptually that this extends forever in all these directions, right? It's a flat sheet. It's flat. It always has, there's only one direction that's always normal to it forever. However, when it slices through the first octant, it passes through 2 on the Z, 3 on the X, 6 on the Y. And that's all there is to sketching planes. Okay. Now, planes are a kind of cylinder. Normally when people think of cylinders, they think circular cylinders, but cylinders are actually way more general, and I'm going to talk about that now, and I'm actually going to show you how to sketch cylinders. So planes are a kind of cylinder. They're a weird kind of cylinder. We now look at non-planar cylinders. So if you have a cylinder that's not a plane, how do you go about sketching that? What is that even? Okay, so that's, now we've officially started 12.6. So yeah, in the last section, we looked at planes. No, we did not. We skipped that. Okay. So cylinder, intuitively what a cylinder is it's created by taking some curve called a generating curve and propagating it uniformly along an axis. What does that mean? If you pass an infinite number of lines through that curve along its entire body and force all these lines to be parallel to some other line that we call the axis, those lines will form a surface, and this surface is called a cylinder. You don't really need to know the definition as technical as that, but I do want you to understand the idea. The idea is the following. I can have any one curve, a generating curve. So for example, I can have a curve that looks like an integral sign. And what I'm going to do is I'm literally going to move this curve along some axis and trace out the surface it creates in space. So I can say, just move this guy, undo. Let's say along some axis over here. So literally, no matter where I slice, it's the same curve that's always being shown, right? And so I take one curve, and if I drag it along an axis, so the axis here is this way, then the set of points in space that the curve would actually pass through, that is called a cylinder. I don't like how that's. Okay, so that's called a cylinder. So that is what it is conceptually. Now, how do you recognize a cylinder and sketch one in terms of a formula? So for non-planar cylinders, two things are common to all of them except planes. So one, you have one variable missing, i.e., equation will have only two variables. So once you see an equation where there are only two variables, think of it as a cylinder, as long as that thing is not a plane. So I am emphasizing here it's non-planar, right? So I mentioned that as a plane is a weird kind of cylinder, because here it's a cylinder where you can have that cylinder and three variables are present. For any other cylinder, you will never have three variables present. You will have two variables present, right? So there'll always be a missing variable. So that's the one thing. The next thing is that the axis will be parallel, the axis of the cylinder will be parallel to the axis of the missing variable. That's the next thing. I would also, I guess a third thing would be helpful for you to realize, and that is the equation drawn in 2D gives the generating curve. Okay, so that is an example of a cylinder. Let me give you another example while we're just here. So example, y equals x squared. Ask anyone in Calc 1 or below, they'll tell you that's a parabola. We now know better. In 3 dimensions, this is a cylinder. It's not a parabola. How do I know it's a cylinder? It has two variables. There is a missing variable. Which one's missing? The z is missing. So, boom. Maybe it's down a little bit. This is a cylinder. Notice only two variables. Z is missing. So we're, so axis is parallel to the Z axis. Also, the curve y equals x squared in the plane of the other two variables, the xy plane, is the generating curve. So this brings you to the first major lesson. The trick to being able to sketch something very nicely in 3D is to be able to sketch things very well in 2D, which is the whole reason why I went over conic sections, as we're going to see. So what I would do is realize here that, well, I know what y equals x squared looks like in the xy plane. That's just this guy. So that is your generating curve, which means if I go to 3 space, what am I going to see? in the XY plane, that generating curve is going to be there. Right? Now, because there's no Z present, that's the curve for all values of Z. So no matter what level I'm on, that is the same curve I would see because the Z isn't present in the equation. What this ends up meaning is that no matter what level of Z you're at, the same curve is going to present itself. So if I move up, the curve is going to be there. If I move up further, the curve is going to be there. If I move down, the curve is going to be there. And what you're going to realize is this is going to create a surface. And so it's like something that's opening like a parabola, but it's actually running along an axis. So it's like I took the parabola in the XY plane and I slide it up and down the Z axis. That's a cylinder. So once we know how to draw, and probably, I don't know. I'm thinking I should have did these ones in another color. Is that going to work? Maybe this might work. I think I need a keyboard for this. Still going to take forever. I want you guys to see the generating curve a little bit more. So I'll just leave it highlighted. Okay. So you draw the figure in 2D, run it along an axis, boom, you have a cylinder. How do you know it's a cylinder? There are only two variables in the equation. What axis do you run it along? See the missing equation? Parallel to that guy. And voila, that's a cylinder. Everything I said, I typed it up here. So you don't have to read that right now because I pretty much rewrote the thing and explained it here. Let's do another example just for fun. X squared over 9 plus Z squared equals 1. That is a cylinder. How do I know? There are only two variables present. Who's missing? The Y. What direction should it stretch in? Well, parallel to the Y-axis. That being said, this equation x squared over 9 plus Z squared equals 1. If I were to sketch that in the XZ plane, what would that look like?
An ellipse.
It's an ellipse. But we know how to sketch those now. It's an ellipse that stretches more in the X direction, right? Which means Now, if I look at the XZ plane, there is a guy that looks like this, right? And I even know it will touch the X at 3 and -3. And it will touch the Z at 1 and -1. And it runs along the y-axis. That should be like a parallel kind of. So that's your generating curve, but now you realize that this is just the same curve over and over. So this is what's called an elliptic cylinder. This one is called a parabolic cylinder because it's a cylinder created by a parabola. This cylinder was created by an ellipse called an elliptic cylinder. So pretty much there's going to be an infinite variety of cylinders, right? Pretty much every curve that you can think of can create a cylinder if you just decide to drag it along some axis. So any 2D curve you think about, you can create a cylinder with that curve. So there's an infinite variety of cylinders, so I can't really tell you about all of them, but here are some common ones. The parabolic cylinder. Notice here that the generating curve is a parabola, and here it's running along the y-axis because this is the curve z equals x squared. The y is missing, so it's going to be a parabola running along the y-axis. Here, x squared plus y squared, we actually already looked at that. So that's like a, maybe a green. There's going to be like a circle. But it's a circle at every height. So it's running along some axis. Which axis? Well, the z-axis. How do I know the z-axis? Because x squared plus y squared equals 1 only has 2 variables in it, and the z is missing. Similarly, hyperbolic cylinder. This one comes from a hyperbola. A bunch of hyperbolas, and they are running along the x-axis. So you should recognize that y squared minus z squared equals 1 is a hyperbola. It opens towards the y because we know how hyperbolas work. If you were to sketch in the yz, then because the y is the positive one, it's going to open towards the y. And that gives these green curves here, right? So in terms of cylinders, I can't give you an exhaustive list of all cylinders. There's an infinite variety. And so it just comes down to being able to sketch it in 2D first, then you just propagate that sketch along an axis. So that's pretty much cylinders. That's how you recognize them. That's how you sketch them. Now, the next thing this section covers is something called quadric surfaces. Now, it turns out there's a finite number of these guys. And what these guys are, it's a 3D generalization of the conic section. So you think of, if we could visualize a 4D cone and we could slice it in 4 dimensions and look at the outline in 3 dimensions, the surfaces that we would see in 3 dimensions is what's called a quadric surface. And so that's why I went over conic sections with you, because to draw the quadric surfaces, you'll need to know how to draw the conic sections. So in terms of an equation, quadric surfaces have this form. I guess instead of thinking of them as a generalized conic section, which might be weird if you don't know about thinking about 4D is difficult, you could think of them as a generalized quadratic as well. The highest power of any variable is 2. So you have the first power, the second power, the first power, and the constant terms. Normally, we can do like some sort of shift or transformation to write a conic section in this form, right? So there's a general form here, but we can often, through some sort of transformation, write it as this form. And so we really only need to know how to graph this form for some constants A, B, C, and J, right? So for example, x squared plus 2y squared minus z squared equals 1 is an example of a quadric surface, right? It turns out there are only a finite number of these, so I can actually tell you exhaustively how to sketch quadric surfaces. There will be 6 of them that you'll be able to sketch. And I'm going to show you how to sketch 6 of them. Now, conceptually, this is done in much of the same way that I was doing here, first doing a 2D sketch. However, to sketch the quadric surfaces, you're going to need to be able to do several 2D sketches. These sketches are called traces. It's kind of like a higher dimensional analog of finding all the intercepts and connecting them. To sketch the 2D surface in 3D, what you're going to need is to find a bunch of boundary curves and then kind of combine them together. And you'll notice that when we slice these guys, parallel to some of the coordinate axes, the result is always going to be some sort of conic section. And so it turns out that we're going to need to be very good at conic sections. So it turns out these equations here tells you that what you're sketching is a quadric surface. You'll notice that these guys just amount to us choosing constants A, B, C, and J. So for example, for the first one, which is the ellipsoid, which is the one I leave circled here, that is what we would get if I choose A to be 1 over A squared, B to be 1 over B squared, C to be 1 over C squared, and J to be minus 1. I get an ellipsoid, right? Okay, so these are the equations. And on one hand, you could just memorize them and just know that this is what they are. On the other hand, a lot of times, even I can't tell you off the top of my head what these guys are. I just sketch them off the top of my head by sketching the 2D sketches and putting them together. So there are some that I would recognize right away because they show up just so often, like an ellipsoid. It's very easy to recognize. It's kind of like the equation of a sphere, except the coefficients of the square terms aren't all the same. Cones you'd also recognize because it's going to be 1 squared equals the sum of squares. So there are things that show up all the time, but there are ones that don't show up very often, like this guy or that guy, in which case, even I don't remember them off the top of my head. If someone were to wake me up at 4 o'clock in the morning and say, what's the equation of a hyperboloid of one sheet? I don't remember. Is it 1 negative or 2 negative? I don't remember. But I could sketch one if you gave me the equation. And why can I do that? Is because I'm really good at sketching in 2D. And that skill will translate. And it translates through this idea of traces. So traces is basically doing the following. You're going to sketch something in 2 variables at a time, but you're going to sketch it with all the pairs. So you're going to sketch what does it look like in the XY plane, or in some plane parallel to the XY plane. What does it look like in the YZ plane? What does it look like in the XY plane, XZ plane, etc. Once you get all these curves, you put them together. And how do you get these curves? You would plug in 1 variable equals 0 at a time. So instead of plugging in 2 variables equals 0 at a time, which will only give you a point, you want to plug in 1 variable equals 0 at a time, or you can plug in 1 variable equals some convenient constant. So let me demonstrate with this guy here, which probably not now since I just introduced it, but definitely by the time the final rolls around, I expect you to look at that and just know that it's an ellipsoid. However, how would I go about drawing this ellipsoid? Well, we would do the traces. So what is the trace? You sketch the 2D curves in each plane. So let's say we're in the XY plane versus the YZ plane versus the XZ plane. So I'm going to do a bunch of 2D sketches. And I only really need to do enough so I can understand what's going on. So in the XY plane, what does that mean? That means Z equals 0. In the YZ plane, that means X equals 0. In the XZ plane, that means Y equals 0. So I'm going to go to the original equation. I'm going to plug in one variable equals 0 at a time. So if I plug in Z equals 0, what do I get? I get X squared over 4 plus Y squared over 9 equals 1. And what is that?
That's an ellipse.
Ellipse.
Then that's an ellipse. Where does it stretch? Where's the major axis?
Along the y-axis?
Along the y. It stretches more along the y. So this is it's elongated that way. Center of the origin. If I plug in X equals 0, I would get Y squared plus Y squared over 9 plus Z squared equals 1. And what's that?
Also an ellipse.
It's also an ellipse. Where does it stretch?
In the y direction.
Also in the y direction. In fact, I know that it goes 3 along the y and 1 along the z. And I would also know that this one goes 2 along the x and 3 along the y, right? Because we did conic sections. I would come over here, and now I'm going to write xz. What does it look like in xz? Well, that would look like x squared over 4 plus y z squared equals 1. Notice that is another curve. That is another ellipse, but this one stretches in the x direction. So this one stretches 2 units in the x, 1 unit in the y. Let me color code these things so you can see what I'm going to draw, because we're gonna put these guys together to get a 3D sketch. So the idea is we draw a bunch of 2D sketches to figure out the 3D sketch. Now, of course, if the point is to draw a 3D sketch, then the 2D sketch isn't the goal, and you want to be able to do the 2D sketches very quickly so you can get on your way to drawing the 3D sketch. And with enough practice, so especially to start off, you might draw the traces separately. So here I draw 3 separate curves and then I'm going to put them together. But with practice, you should be able to actually do this all in one spot. So what we do now, we're going to sketch a bunch of, I don't know if I'm going to get through all of these, but the principle is going to be the same principle that I'm using throughout. I'll just do a few examples for you guys to see. So what I would do is, now this comes down, and now I'm going to put all these guys on the axes. So let's do the first one in the XY plane. It's an ellipse. I'm going to sketch that in blue. So this one stretches along the Y. I know it hits 3 over here and minus 3 over there. It hits 2 over here, minus 2 over there. Then I have in the YZ plane, so I'm imagining this is on the wall, on the YZ wall. and it's also an ellipse. It hits 1 on the Z and -1 on the Z. Do I want to? And then I look at the other one. It's again an ellipse in the XZ. So that one is green. It's going to be da-da-da-da-da-da. Da-da-da-da-da-da. No, it passes through that too. So now you kind of see the skeleton. There's like this wire frame around the thing. And of course, now you just put some meat on that bones, on those bones. So now you see that there's an ellipse here. And I put it together from that. Now, eventually, you will be able to like draw all of these all at once soon. With practice. So you can actually see the equation x squared over 4 plus y squared over 9 plus z squared equals 1. And then you'll be able to just go in and be like, okay, so here are my axes. If I take my finger and cover up the Z, I realize that I have an ellipse in the XY. Take my finger and cover up the Y, I have another ellipse in the XZ. Take my hand and cover up the X, I have another ellipse in the YZ. And so you can sort of put these together immediately and get an ellipse. Right, so that's how we get the first figure right here. It's called an ellipsoid. Right, so there are 2 levels. You can draw a bunch of traces, put them together, or when you get to pro mode, Hokage level, you can actually just draw the 3D axes right away and draw your traces directly on the axes. It's kind of like those students who, when they're drawing piecewise functions, some students have to draw it one at a time and then erase pieces and put it together. Versus when you really understand a piecewise function, you literally can separate in your mind where you're drawing which part of the graph and just do it all at once. Takes practice though. So like I said, this is not going to be hard, but it is something that's going to take practice because you're not used to doing it. But at the end of the day, we are doing things that we know how to do already. We're just doing 2D sketches, and then we're kind of putting them together in some kind of 3D form. Any questions on this idea? Okay. So we are going to do this. But as it is already late, I wouldn't fault you guys for having to leave. So I guess what I will say at this point is to just do sort of a farewell. Hopefully you had a lot of fun in this class. Hopefully you enjoyed yourself. And I wish you good luck in your finals to come and all the best in the future. And if I never see you again, all the best. But I will see you again next week probably because your final is on Monday. If you have to leave, I would say you have to leave. You can leave. What I will do is I already taught you all the principles you would need for this, but I think more examples will be in order because I'll be talking about this on the final. So what I'll do is I'll just hang around and do these guys. If anyone wants to stay and watch me, you're very much welcome to. But of course, if you have to leave at this point, I will understand. Have a good night, have a good life, and I will, I guess, I don't know, as always, see you in the next one.